Hello, everyone. Welcome to another episode of Manufacturing Matters, the podcast where we talk about the trends and technology shaping the global industry, logistics, and other sectors of the economy. I'm Dan McCarthy of Tech B2B Marketing. Joining me today is my guest, Arne Leinse, CEO of LioniX International, a leader in the development of MEMS and photonic integrated circuits, aka PICs. Welcome to the podcast, Arne. Thanks for joining us today.
Thank you very much, Dan.
So we are a little bit on the frontier of where we typically talk about manufacturing in this podcast. We're sort of on the frontier of semiconductor industry, if you will. So let's kick off with a little context. PICs, photonic integrated circuits, are, to my mind, the manufacturing story of the century in that they actually make semiconductor fabrication, already a manufacturing moonshot, seem almost simple by comparison. So before we dive in, tell us a little bit about what makes PICs so challenging to produce and what benefits could possibly justify all the investment, innovation, and risk that goes in their manufacture.
Okay, I wouldn't say that semiconductor manufacturing is easy compared to PICs, because semiconductor manufacturing is difficult and has its
Fair.
own problems and its own issues. So the main issue that with integrated photonics manufacturing, the issues are different. So indeed, we use photons instead of electrons, which all of a sudden means that the um, dimensions are also different. We are not talking about transistors or small electrical features. We're talking about long interaction lengths. A waveguide, which is crossing a full chip, has a long interaction length, a very narrow line width, but it should be defect free over a long path. So that all of a sudden has different issues in your lithography, in your etching, in your planarization of everything. So it's different. I wouldn't say it's more difficult or easier. It's a different game, which is indeed picking up. It's compared to the semiconductor industry, relatively new. We are, in that respect, several decades behind the mature semiconductor industry, but we are
Mhm.
picking up and we are learning from the lessons that the semiconductor industry has done before.
And just to get back to what are some of the benefits of PICs? What do they introduce that semiconductors alone cannot?
Well, the nice thing is, if you, for instance, talk about signal processing in the what is standard usage of telecom wavelength, 1.5 micron, which has a frequency of 193 terahertz.
Mhm.
Which is a very high frequency, is all of a sudden you want to process small frequency bands of several gigahertz or 10, 20, or 50 gigahertz. Those kind of frequency bands are, if you transfer them to the photonic domain, actually very small ripples, which are easy to process. So in photonics, you can all of a
Okay.
sudden do processing, you can do signal transport, you can do things which in the electrical domain are either difficult or impossible. So it's not a replacement of electronic technology, it's an
Right.
addition with new functionalities.
Okay. And so you're adding photonic components to a chip package, sometimes with ASICs and semiconductor chips themselves. What is so complicated about integrating photonics into that?
Well, it's more in standard ICs, the features are small, but the bond pads are large. And what I mean with large is compared to a cross section of a photonic integrated circuit. So where
Right.
photonic integrated circuit, you need to get the light in and you need to get light out in some way. And if you don't do perfect overlap, then you lose photons, and you can lose a lot of photons if you don't
The
do it
alignment
carefully.
issue.
So all of a sudden you have an alignment issue where alignments of in the order of 100 to 200 nanometers are critical, and then in multiple dimensions. And I didn't say that
Right.
electronic assemblies are easy, but at least you have
Right.
different, less degrees of freedom, and your alignment tolerances are less critical.
Right. Okay. And that like I said, this is sort of a manufacturing issue to me. This is why I think PIX is still, it's for all its benefits and all its advanced technology futures, it's really comes down to a manufacturing issue, which is scale,
I agree.
which I'd like to get into next. Go ahead. Okay, good. We're in alignment, so to speak. Um, so before we go into that, though, tell us about LioniX now. Where does it fit into this value chain, and what makes its role unique and important?
Yeah, so we actually started out as a chip making company, so an mixture between an engineering house and a chip making company in photonics and MEMS. And over the last
Mhm.
decade, we transformed it to a vertically integrated company where we do not just make our own chips. We also do the design, we build the modules, we do the electronics, we do packaging and assembly of that full module to supply customers with a module with a certain functionality and not just with a chip. And you see, particularly in the new markets like integrated photonics, there are no standards yet in how sorry, to integrate a chip in a package or to combine chips or different platforms together. So customers that use this technology, um, they need to be helped and they need a solution to be provided to them. That's the reason why about a decade ago we made the decision to become vertically integrated, to not only make the chips but also deliver functionality in a box. So we're not a pure play foundry. We are a module supplier using PICs and then in particularly silicon nitride based waveguides.
Right, which I want to ask you about too, because that is one of your proprietary technologies, silicon nitride. And just because it's a little bit, again, unfamiliar to some of our listeners, that's part of the waveguide that guides the light, and it's a
Yeah,
particular material. Can you tell us a little bit more about that?
yeah. So in just to go back to waveguide, everybody knows what a fiber is. We all have seen these decoration fibers where light comes out. If you bend them
Right.
too much, the light will leak out, and you will see it at the edge of the fiber. Integrated photonics is not different. You just put those fibers on a chip and you do the signal processing on that chip. And there are different platforms that have matured over the last years or last decades, actually. Um, um, well known for the silicon photonics that is used a lot nowadays in data centers, all based on silicon waveguides. You see a lot on indium phosphide. Indium phosphide is
Mhm.
particularly good to generate light and do fast modulation. And you've seen in the last years, or actually the last 10, 20 years, also a strong development in silicon nitride. And silicon nitride is actually maybe that's even the best mimicking of that fiber. It's a passive waveguide on a chip
Mhm.
where you can do all sorts of signal processing with low loss. That's the big benefit of our waveguide technology, that you don't lose a lot of photons and it is transparent also over broad wavelength range. So where the traditional technologies that are developed for telecom, they work in infrared in the telecom wavelengths that are used historically. Silicon nitride can also handle, for instance, visible light, which makes it all of a sudden an interesting material to use
Mhm.
for new applications like AR, VR. If you want to project light and if you want to do direct projection in the eye or on screens on your glasses, it helps if your waveguides can transport that light signals. And their
Right.
silicon nitride is a very unique proposition.
Right. So it minimizes loss, but it's also, correct me if I'm wrong, but because it's sort of based on silicon, it's a little easier to integrate than some of the other materials out there, the more exotic materials, if you will, that guide light. Would that be
Uh, uh,
correct?
I agree. I mean, since it's on a silicon carrier, it's very robust. I mean, if you handle an indium phosphide wafer, be careful with it. Don't sneeze too hard, or it's very fracture. It's fragile. You can easily
Right.
break it if you handle it wrong. Yeah, silicon wafer you can drop on the floor, pick it up again, it's still intact.
Okay.
But that's the big benefit of that. Once your wafer reaches to the end of your process and has high yield, it's very robust also in the packaging and assembly afterwards. And
Okay.
that's of
All
course
right.
that you benefit from a long history of silicon processing. Silicon has been used standard in the IC industry for a long time already.
Right. But silicon neither produces light nor does it guides light with limitations, mostly infrared. So um,
Yeah.
not an ideal solution for guiding the light. Electron's great. Guiding or electrons not or photons not so much. Um, the thing we talk a lot about in this podcast is the challenge of scaling up from prototype production.
Yeah.
It's a particular challenge for PICs, as you pointed out. You have to design the chip, and then you have to integrate that chip into a package that can then be put into a system. But can you dive a little deeper into the manufacturing hurdles when scaling PICs for higher volume markets, like data centers, for example?
I can, although you actually just used the wrong example there.
Okay,
And what I mean with that, no, but the data center is actually the easy one to scale because
that's a good point. Yes,
that's one of the few applications where the volume is there. So, and if you have
right.
volume, the business case of putting a production line in place and making it is relatively straightforward. What you're seeing is the silicon photonics is run standard a lot on the standard silicon lines of CMOS fabs or of electronic fabs, and therefore it's
Mhm.
easier to do scalable production there. And those volumes are there now, so there's no justification, there's no question about investing there in tools and in production equipment. The other platforms, like silicon nitride, for instance, the volumes are not there yet for all the other applications. Actually, data centers is one of the few that makes it to high volume already. The rest is coming. And there, the main challenge is a bit the chicken and egg problem. Do you
Right.
put a high volume fab there to be able for these applications to, or to enable these applications to be realized? or do you first want to wait till the volume is there until you build a fab? But building a fab is costing
Right.
you 2 years, so then
Right.
you're too late. So the challenge there lies in having scalable production volumes, and therefore it lies in how can I set up a uh, medium volume production, or how can to start delivering to the market at the volumes that are requested for the coming 5 years, and how can I combine multiple applications in one platform. So how can I do low volume, high mix by use standardizing cross sections, standardizing processes, that you're not just making chips for one application, but in that same production line, you can make chips for a lot of applications, all in the same process. And therefore, all these
Okay.
smaller applications, they add up to fill your fab, because the only way how you can run a stable fab is by running it, by doing production, by doing volume production, by starting as many batches, as many waves as you can, because then you get statistics and you get a stable process, and then you can deliver in the end known good die.
You're right, and you're right to correct me on the chicken and egg problem. Data centers is the high volume one. That is where there is demand in order to sort of support the production of PICs economically. But let's look at some of beyond data centers. How do manufacturing requirements for other applications compare to those end markets? How do you what are the demands on the chips that are different that make it harder for those to scale up?
Well, the biggest demands you see there is particularly the newer applications, like satellite communication, like fiber optic gyros, like visible light application. They all have a very a quantum is one of the application domains, but that's very stringent demands for the photonic integrated circuits. So there, the propagation losses are critical. You need to really, you cannot
Mhm.
lose, I don't say any photon, but as little photons as possible. So the critical steps in your fabrication process are way more critical in that than in the maybe more forgiving um, uh, data center application where you have smaller chips. And I'm not saying the data center applications are easy. At least the chips are
No.
smaller, and you can tolerate slightly higher losses than, for instance, in a quantum computer or in quantum sensing.
Okay. And as losses become more stringent, obviously the alignment issue becomes more stringent, and that takes more time in the
Exactly.
process. So,
Yeah.
um, does serving? I mean, I'm not sure if Linux is positioned to serve multiple markets, or if you take all comers, you focus on one market, like the high volume data center type applications. But does serving multiple markets force trade offs in your process capabilities, or does your platform approach accommodate that?
No, actually, we've always been around by serving multiple markets,
Okay.
and that's not because we Um, main reason why we did that is because the platform allows to. I mean, we're transparent from this nitride is transparent from 405 nanometers to 2.35 microns, which has everything from visible light to the standard telecom window, and even slightly behind that, or
Mhm.
slightly higher than that. So that means that applications like AR, VR, biosensing, LiDAR, fiber optic gyros, OCT, data centers, microwave photonics for satellite communication, that broad range. The nice thing is for silicon nitride, they're all the same. And of course, it's not that straightforward, but the fabrication process you use for all of them is not different. We standardized long time ago the cross sections as much as possible, and we called that design by geometry.
Mhm.
We don't play with the process. We just play with thickness and width, and of course the layout customers can play with, but we are not reinventing the fabrication process for every application. And then you can indeed have a broad range of applications. And of course, for specific wavelength ranges, you have your standards. We're not reinventing a waveguide cross section for an application that
Okay.
is 10 nanometer higher in wavelength. You get the same as the one 10 nanometer lower, because in that way you can build up statistics and you can indeed combine multiple applications in the same cross section, and generate that volume even from the beginning already.
Understood. Okay, and this is what part of makes picks so interesting to me is these sort of engineering trade offs in the manufacturing process to kind of keep that flexibility, but
It,
also
it
keep.
picks are nicely at that intermediate transition between um, the technology push, the academic users, and the real the early adopters who use PICs 10, 20 years ago. Where now
Right.
it's really
Right.
it's picking up and it's getting mature, and It's more about functionality than about exactly what PIC it is. 15 years ago, our customers wanted to know what exactly the cross section was and what the chip looked like, and now they want to know what does it do.
Yeah.
And can you make it reproducible? If yes, fine. How many can you sell me, and what does it cost? And that's a different discussion, and that's where also your fabrication process and your tooling and your equipment needs to align to.
Okay. Next exciting time, I think, for the industry. I'd like to get back into standardization in a minute, but before we go there, I'm curious what quality control looks like for photonic integrated circuits. It's a big
Mhm.
discussion for anyone in manufacturing, inline inspection, functional testing. You're testing, and if you're at the package level, you might be testing for both electronics and uh, photonic signals. So I'm just curious, what are the challenges there for testing and functional testing? Hello, everyone. Dan McCarthy here. Thanks for listening to the Manufacturing Matters podcast. Don't go away. We'll get back to it in just a minute. I wanted to take a quick break to let you know that Manufacturing Matters is sponsored by Tech B2B, a full-service PR and marketing agency specializing in industrial automation and electrical and photonic systems. Our services include media relations, content development, website development, including SEO and generative engine optimization. We can help you optimize your CRM and get your digital marketing and lead gen up to speed. And we offer graphic design, animation, and video production. If you ever want to scale up your marketing efforts or accelerate them before a new launch or just have a quick consult, check us out at techb2b.com. Thanks again for listening. And now back to our conversation.
Main challenges are that with a lot of photonic features, and the proof of the pudding is in the eating. So a lot of things you can, particularly if you make things the first time, or the first few times, you can only see where it worked once you've finished it completely.
Right.
The more you start making the same, you can start translating, hey, what measurement can I do in the middle, and how does that translate to my end result? And also there, ideally, you want to do as many photonic measurements as you can, because electronically you can measure a lot. And of course, in the standard manufacturing process, you
Right.
do your visual inspection, you check your defects, you check your, even nowadays with AI, you check your full images of your image recognition of your wafers, and you can find your defects pretty clearly already. Um, but you also want to do some probing halfway and translate what you've measured there to the end result. And any measurement you can do early in that process to determine which chip yields a known good die is a good one. Whereby the frustrating thing or the challenging thing in integrated photonics is that um, the real measurement can only be done once it's completely finished. And as said, the moment you start going into production, that becomes easy or
Mm-hmm.
more easy.
Mm-hmm.
Because then you make multiple times, continue constantly the same design.
Right.
You can translate that layout to measurements you do in the middle. The moment you
Okay.
start, particularly in that low volume high mix, um, you need to really be careful on measuring the process control features in that process and not the specific chips that are in there for the application. Because those application picks, they are low volume. It could be different, could vary from run to run, but you
Mm-hmm.
need to make sure that you create your volume by creating correct process control features that always translate into the same performance, and always give you the same result that you can interpret somewhere halfway down the process.
Okay. Is that more challenging for high mix, low volume chips? Because you have to sort of, it sounds like you
Uh,
have to sort of get the performance down first, and then you can know where to measure. Sounds a little trial and
Well,
error.
it's more challenging if that's why I said you should not measure the real functional device. That's also not what we do with our customers. Um, if we want to check whether a process went well, we check process control features. We have test chips, we have features on there that show us, yeah, the process went according to spec.
Mhm.
And if we then know that spec, and if we know it meets that spec, we can also design basically first time right, because we know what the deviations are of a process. We can manage that, we can measure that. If within that deviations we can simulate that the chip for the customer will work, then we
Mhm.
can also be confident that it will work. Because the complex thing very often is that it's not more and more you get more complex layouts of chips that need a full calibration file to set. You cannot measure that during processing. You can only do an assessment early on, and that's where vertical integration comes in the picture, because it's not just making a chip, it's also
I see.
making something that's robust, designing in a robust manner that you have your process variation designed in your layout. And if you then know that what you've made is within your design variations, yeah, then you can also be sure that what you've made will work for your customer. And then it doesn't matter anymore what the functional chip of the customer is, as long
Right.
as it is designed within those limitations. And that's some customers or engineers always want to push the boundary. Oh, but if we could do this, then we get better performance, but it's less robust. And there you have to move them away, saying no, stick within the robust ones. If you want to try something new, then first validate those building blocks in a more robust environment, and then you can translate them into still working.
Understood. Getting back to standards, we talked a little bit about why they're important to the efficiency in the manufacturing process. I'm just curious, industry wide, the early semiconductor industry sort of had to evolve its standards in unison, right? Through they sort of monolithically moved forward and implemented standards on common interfaces, protocols, component libraries. Are PIC designers, equipment makers, and foundries attempting something similar now? Is standardization moving forward monolithically, or is there a path for individual companies to sort of establish that as well? And where's that divide?
There's not one golden standard there. There is, however, more and more the last years a trend towards standardizing interface. Same as what you
Okay.
see, like you described in the IC industry. Um, the interface on the fiber side is nowadays standardized. What you do there, how you have alignment loops in there, how you package it. Um, However, the interface of one platform to the other, for instance, is not standardized yet. So there in our platform, we can adapt mode profiles and pitches and angles and everything to the other platforms. There's not one golden standard yet for transferring from one platform to the other. There's still missionary work to do there, so to say.
Mhm.
And that will come, that will happen, because you see more and more hybrid and heterogeneous integration. You see more chiplet integration or piclet integration of active components on platforms. And that means that if you want to mix and match different platforms, you will also see automatically that standardization is enforced there um, by the by the applications drizzling down towards the foundries, because it's in everybody's benefit if you have a standard on a cross section or a standard on an interface.
Okay, so that's industry wide. How do companies like LioniX improve your internal efficiencies and standardization without compromising flexibility? We talked about this a little bit earlier. We talked about the high
Yeah,
mix.
and well, that's exactly why years ago we froze our cross sections, we froze our fabrication
I
process.
see. Yeah.
That doesn't mean we do not keep on tweaking and optimizing it, but not in customer batches. We don't do that. In the early days when we just started, every batch of a customer was different, because our engineer, oh, if we do this better, we could improve the performance. Nowadays,
Okay.
we say, don't do that. That's our workhorse. We run that. In parallel, we got
Right.
parallel lines where we do optimization. We validate stuff. But if you've done it over a number of times, then you can bring that optimized process into your main process. And there, so you need standardization. You need to fix things, but you still need
Mhm.
the playroom to and that's the reason why a company like ours, we do product development and small volume production also for our customers. The moment you go into a high volume production fab, that flexibility, of course, is less.
Right. Right.
And
Right.
that's also
Manufacturing
the
drives
sweet,
design.
exactly. That's also the sweet spot where we are. We are in the transition from module to small and medium volume. For the wafer fabrication, once it becomes real medium volume, we transfer it to a medium volume foundry or a high volume foundry. We get the chips back and we build the modules for our customers based on that. But you need to make sure that you can handle that standardized process, but still have the freedom to try new things in parallel fabrication runs and parallel production lines.
And this is where your vertical integration is a benefit.
Uh, the vertical integration is a benefit because the tricky part is it's not just in a photonic integrated circuit. It's in the end, the performance is in the module. Performance
Right.
is in how well do my chips connect to it, how well can I assemble it, how robust can I assemble it, where are my reference planes, What's my wafer bow? Do I have some smile in my chip or not? If I connect the other chip to it, hey, if I do this and maybe make some stress release there, my assembly becomes way simpler. So all those kind of tricks help if you also face the problems in the end. I mean, if you just make the chips and you let somebody else figure out the packaging, yeah, then it's solved, and engineers are creative; they can solve it, but maybe not always at the most elegant or more cost-effective way.
Understood. So that's your internal structure is giving you some flexibility and standardization there. I'm curious, where is the limit of that? And really, maybe you phrase that a little bit. What are the external? How important are external forces like governments, industry consortiums to sort of the overall success on standardization? Where do they come in? What's the value?
Good point, good question. The main point there is that what we see happening, for instance, in the Netherlands, is and you see that happen more across Europe also,
Mhm.
is that integrated photonics and process design kits are appointed as a key enabling technology. It's important to the market. There are different research programs in standardizing the platforms, enabling process design kits to be fabricated such that users can also access technology, and
Mhm.
multiple of these PDKs should be able to work together in building multi-PIC solutions for customers. Um, the government there has a role there in by facilitating or by um, pushing forward these kind of developments and enabling them by because if you do it as just one party, you can try to set the standard, you can try to build these kind of things, but if the rest doesn't follow, it doesn't work. If you really want to make sure that I can make standards in, for instance, a silicon nitride chip and indium phosphide chip,
Mhm.
it helps if the indium phosphide chip speaks same language. Then it helps if you got development programs and where all partners are connected with the software vendors, with the also with the design houses in the end. That in the end everybody speaks the same language and says, hey, if we do this, it enlarges the application domain in which we can use these. Well, then it can drizzle down into the foundries, into the designers, into the PDKs, and that only works if you work together. If everybody wants just to do its own business or its own product, then you
Right.
solve your own problem. But
Over and over.
and that works very well for a lot of companies, for a lot of things. But if you are a platform, you do a lot of technology push, and if you're a platform developer, yeah, it helps if you have input from a broader range, and that the rest of the components that we need in our platform, or the packaging that we need, or that at least they obey the same design rules.
Yep. Okay. That makes sense. We've one of the questions I was thinking about is this is it's not as specialized as maybe I made it out to be earlier, but workforce, is there a particular profile of people that if you're drawing in from other industries or people specializing in this in their education now? I mean, how hard is it to find qualified workers in this, both based on the educational output as well as today's market? Is
The
that
good
a
thing is,
challenge?
yes and no. The good thing is that nowadays it's a global market. So we currently we
Mhm.
are around 70 people. We have 15 nationalities within the company. So we are very lucky that we can still find good people. We can still hire good people. And for the different disciplines, it varies what skills you need. Some people are
Mhm.
I like them to be able to handle a set of tweezers that you know how to pick up a wafer or a chip. And some
Right.
are should be very good with designing, and we need all of those. But the main thing is that what we've seen change over the last years is particularly that our hiring process is more a global process nowadays, or
Interesting.
A European slash global process than in the old days where um, all your employees already lived closer to the university here or to the companies here, and that really changed over the last 5 to 10 years. Our company indeed where as said, we now have a multicultural company with a lot of nationalities, which is fantastic. I think it
Mhm.
really brings something to the company if you get that diversity within the company. Um, and you see that there's really good talent also coming from abroad.
Did that trend coincide with your shift into PICs from MEMS? I mean, did you start to go more global as you got more photonic,
No,
so to speak?
no, we actually we actually started with photonics back in 2001.
Oh, okay,
So we started in January 2001
interesting. Okay,
as Lion Photonics back then. But the telecom bubble bursted in actually that same month or the month after. So all our customers went bankrupt in that first period. And then we started adding MEMS and microfluidics. And since then, we've always been doing MEMS, fluidics, and photonics. Where
okay,
the in those early years after the bubble bursted, the MEMS and fluidics were the dominant work we did. But the photonics never faded out because when the bubble actually bursted, we said we need to reinvent the photonics because the platform we worked on then was not scalable, was not volume manufacturable. And we really went back to the drawing board. So how can we make it with standard equipment, something that's reproducible and volume manufacturable? And that's where our triplex platform also came from
I see.
by using standard industry from the solar cell industry, standard equipment from the solar cell industry. And so therefore the photonics has never been gone. What we've seen is that particularly that when we grew over the last 5 to 10 years and we needed more engineers, that's when indeed the pool here wasn't refreshing quick enough to get them from local sources, so to say. Sorry,
Hmm.
I don't want to say it like that, but that's maybe from local universities or local schools here. So then the pool gets relatively quickly bigger, and also um, COVID has helped in that respect. That due to all the like we do now, the video conferencing and everything, the world has become smaller. So doing job interviews with people across Europe or across the world is much easier nowadays than 10 years ago when we were sitting around a conference call machine and you couldn't see each other or it was way no, but that it makes applying for a job and also having job interviews easier when you can quickly schedule a Teams meeting and have a quick call with them and just select the most promising candidate and fly him or her over to here to discuss further.
Interesting. Okay, that's interesting. Is there anything we haven't talked about that we've kind of glossed over or under understudied?
Uh, no, well, not necessarily. I mean, we touched upon it how the volume capacity should scale along with the demand, and that's of
Mhm.
course what you see happening now, particularly in silicon nitride. Silicon photonics is traditionally more made into to the electronics fabs that are used to handling silicon insulator or silicon photonics already. They run it in the sideline of their production capacity. Silicon nitride actually, there is no um, dedicated silicon nitride medium volume foundries.
Hmm.
We see that being started now. We see different volumes starting to do either nitride on the side or started as a dedicated nitride initiative, like the New Origin initiative we're putting on a map here in the Netherlands
Mhm.
to indeed build particularly targeted medium volume where what the market is needing for the coming 5 to 10 years. And not immediately aim for we need 50,000 wafers per month because integrated photonics will not be there for the coming years. So
I see.
those are there, those volumes will go up, but not immediately to the high volume that electronics already has.
Yeah, that actually brings to mind a question about supply chain for me. So you're talking about when you talk about photonic integrated circuits as opposed to semiconductors, you're using a lot more materials. You need indium phosphide for the lasers. You need different materials for the waveguides like silicon nitride or others, and then you have other components on their modulators and whatnot. Is the supply chain more complicated for you? Does that present any challenges currently as that changes, particularly with the supply chains
Is,
changing?
is that is that supply chain so much more complicated than in the semicon industry? If I open up a multi-pick or sorry multi-IC package in a semicon, there are also chips from different foundries, different platforms in there.
Mhm,
That
mhm.
that's
Yep.
that's of course not different, although that industry is more mature and running more volume already. So then, yes, they
Right.
all run in different quality standards. They are more used to delivering a certain quality and traceability level. And photonics
Evolving.
is evolving, is catching up there, and therefore you need to make sure. Indeed, that's why you ask about what roles the government have in there. You need to make sure that full supply chain is developing that in that same pace. So that's where the governments have a role there to push those developments.
Mhm.
Because if you can do everything except for one component, you still cannot make your module.
Right.
So you need all
Right.
parties to be on board of that supply chain, and the weakest link there determines whether you can make the product in the end or not.
Correct. And this is where, ecosystems, government-backed ecosystems like, Photon Delta are coming into play.
Exactly,
Right.
exactly.
Okay. Well, I appreciate your time. This has been the most illuminating conversation. Um, I really appreciate all the insights you provided, and thank you for joining the show.
Thank you very much for this interesting session. Thanks.
And for everyone else, thank you for joining as well. I hope you enjoyed this conversation and you found it illuminating as well. And if you want to see it online or see some of our other podcasts, you can find them on manufacturing-matters.com or download them on your favorite podcast platform. I'm Dan McCarthy. Again, thanks for joining me, Arne Leinse from LioniX International. I appreciate the conversation we had today.
Thank you very much.